History of ceramics, from kilns to microchips. The history of ceramics is, in many respects, the history of human ingenuity itself. It represents the very first instance in the archaeological record where humanity did not merely shape a material found in nature, as with stone tools, bone needles, or carved wood, but fundamentally altered its chemical and physical structure through the deliberate application of heat. This transformation from pliable, water-soluble earth into a rock-hard, water-resistant solid marked the dawn of material science. It was a moment of alchemy long before the term existed, the transmutation of mud into stone. While often categorized in the popular imagination merely as pottery or art, the evolution of ceramic technology has been the invisible scaffolding upon which complex societies were built. From the storage vessels that allowed for the accumulation of agricultural surplus, to the fired bricks that protected the first cities, and from the sanitary pipes that eradicated cholera in industrial metropolises, to the porcelain insulators that carry electricity to modern homes, ceramics have been central to the human endeavor. The durability of ceramic material means that for vast stretches of human history, it provides our primary window into the past, a broken shard of fired clay often surviving where wood, textile, and flesh have long since rotted away. The first part of this review provides a comprehensive, deep-dive analysis of the trajectory of ceramic technology. It explores the serendipitous discoveries of the Ice Age mammoth hunters, the industrial scales of Roman and Chinese production, the alchemical obsessions of the Renaissance courts, and the engineering triumphs of the Industrial Revolution. By examining the chemical, social, and economic contexts of these developments, we uncover how a simple mixture of earth and water became the foundation of civilization. Paleolithic origins, ritual, and survival in the Ice Age. For decades, the standard anthropological narrative posited that ceramics were invented alongside agriculture during the Neolithic Revolution to store grain. The logic was sound. Mobile hunter-gatherers would not carry heavy, fragile clay pots. Therefore, pottery must be a product of sedentary life. However, the discovery of the Venus of Dolnichi Vestonice shattered this timeline, pushing the origins of ceramic technology back into the depths of the Upper Paleolithic, roughly 29,000 to 25,000 BCE. This revelation suggests that the first ceramics were not utilitarian vessels for cooking or storage, but symbolic objects of ritual and art created by people who were still hunting mammoths on the frozen steppes of Europe. The Venus, found in the Moravian Basin of the Czech Republic, is a small statuette measuring only 11.1 centimeters in height and 4.3 centimeters in width. It depicts a female figure with exaggerated breasts, belly, and hips, consistent with other Venus figurines carved from stone or ivory during the Gravettian period. However, unlike its carved counterparts, this figure was molded from a sophisticated anthropogenic paste. Analysis reveals it was made from local loess, a fine-grained, wind-blown sediment mixed with water and, crucially, ground mammoth bone. The inclusion of bone ash was likely not accidental. It acted as a temper, a non-plastic additive that improved the clay's thermal shock resistance and prevented it from shattering during the firing process. The technological capacity implied by this figurine is staggering. Scientific analysis of the Venus and thousands of surrounding ceramic fragments reveals a sophisticated understanding of thermal dynamics among these Paleolithic peoples. The artifacts were fired at temperatures between 500 and 800 degrees Celsius. This temperature range is critical. It is high enough to achieve sintering, where clay particles begin to fuse and the material becomes ceramic, but low enough to be achieved in an open hearth or a primitive kiln structure. The mineralogy of the artifacts matches the local soil composition, confirming local manufacture, yet the color variations, ranging from gray and black to oxidized reds and browns indicate control over the firing atmosphere. Perhaps most intriguingly, the context of the find suggests that the process of making and firing these objects may have been as important or even more important than the finished product. Many fracture sections of the thousands of fragments found at the site show clear evidence of thermal shock. This suggests that the figurines may have been deliberately exploded or fired while wet as part of a divination ritual or dramatic performance. The sheer volume of fragments, over 5,000 distinct ceramic pieces found at the site, indicates a dedicated production center, a kiln of sorts, millennia before the first permanent settlements. This evidence forces a re-evaluation of Paleolithic technological capacity. These were not merely opportunistic uses of mud, but a controlled pyrotechnology involving specific recipes, los plus bone, and managed firing cycles, serving the spiritual needs of a community facing the harsh realities of the Ice Age. If Dolny Vestonice represents the ritual birth of ceramics, the caves of East Asia represent the utilitarian birth of pottery. And remarkably, this too occurred long before the agricultural revolution. Recent radiocarbon dating has firmly established that pottery was being produced in China, Japan, and the Russian Far East during the last glacial maximum, LGM, roughly 20,000 years ago. This overturns the long-held belief that pottery required a sedentary, agrarian lifestyle. The site of Xianrendong Cave in Jiangxi Province, China, has yielded some of the earliest pottery sherds in the world, dated to approximately 20,000 Cal BP, calendar years before present. These sherds are from coarse, bag-shaped jars with thick walls, 0.7 to 1.2 centimeters, fired in open-air fires. The paste contains quartz and feldspar temper, added to prevent cracking during the uneven heating of a bonfire. The pottery is primitive, with round bases and rough surfaces, yet it represents a monumental leap in human survival technology. Similarly, Yuchanyan Cave in Hunan Province has produced conical cauldron pottery dating to between 18,350 BP. The emergence of this technology during the coldest part of the last glacial maximum supports the cooking hypothesis. In a frozen world where resources were scarce, the ability to boil food in ceramic vessels allowed humans to extract more nutrients from bones, extracting grease and marrow, and to detoxify plants that would otherwise be inedible. Thermal processing of food in a sealed, watertight container meant that nothing was wasted. The broth could be consumed, and tough fibers could be softened. This survival advantage would have been significant enough to justify the burden of carrying or making pots, even for mobile groups. This technology likely spread or was independently invented across the region. In Japan, the incipient Jomon period, starting ca. 16,800 BP, is defined by the appearance of cord-marked pottery. By 15,700 BP, Jomon pottery was being produced across the Japanese archipelago, associated with a lifestyle that, while still reliant on hunting and gathering, began to show signs of reduced mobility. The Amur River basin in the Russian Far East also shows evidence of pottery by 13,000 BP. These early potters were not farmers, they were foragers who used clay to wring life from a harsh environment. Neolithic revolution, storage, fermentation, and the stability of society. As the climate warmed and the Holocene began, ceramic technology became inextricably linked with the rise of agriculture. In the Neolithic period, starting roughly 10,000 BCE in the Fertile Crescent and later elsewhere, the function of ceramics expanded from simple cooking pots to massive storage vessels. This shift was structural to the development of civilization. The ability to store grain in waterproof, rodent-resistant ceramic containers was a prerequisite for the accumulation of surplus. Without ceramics, grain stored in baskets or pits is vulnerable to moisture, rot, and pests. A fired clay vessel creates a sealed environment. This technological capability allowed for the time shifting of caloric consumption, harvesting in the fall, eating in the winter. It fundamentally broke the hand-to-mouth cycle of hunter-gatherer existence. This surplus allowed for population growth, trade, and the emergence of social hierarchies. Large granary jars became a form of wealth, and the control of these jars likely centralized power. The ceramic vessel was the first bank vault. Furthermore, ceramics enabled the controlled fermentation of beverages. Analyses of lipid residues in pottery from Central Europe and China show that vessels were used for processing milk, storing fish, and brewing alcohol. In China, evidence of rice fermentation in pottery dates back to 7000 BCE. The role of pottery in fermentation cannot be overstated. While grain could be ground into flour using stone tools, the production of beer or wine requires a liquid-tight container for the fermentation process to occur. Porous ceramic vessels, perhaps lined with resin or pitch, provided the ideal environment for yeast to work. Such fermented products were not just dietary staples, they were critical for social cohesion, ritual feasting, and the creation of social surplus used in trade and alliance building. The lipid residue studies from the Ballberg culture, the 4th millennium BCE in central Germany, show a marked increase in dairy consumption linked to specific pottery types like small cups, suggesting that milk and yogurt processing was integrated into the ceramic repertoire. The brick and the city. Structural ceramics in ancient civilizations. While pottery vessels held the food of early civilizations, ceramic bricks held the people. The history of the brick is a transition from the ephemeral to the eternal, driven by the geology of river valleys. The earliest bricks, appearing around 9000 to 7000 BCE in the Near East, for example Jericho, Çatalhöyük, were hand-molded mud dried in the sun. These adobe-style bricks were sufficient for arid climates, but were vulnerable to moisture and flooding. The first major innovation was the mold, developed by the Egyptians and Mesopotamians, which standardized brick dimensions, allowing for more stable bonding patterns and faster construction. Egyptian tomb paintings depict the standardization of this process. Slaves mixing clay with straw, a binding agent to prevent cracking, and pressing it into wooden frames. However, the true structural revolution occurred with the invention of the fired brick around 3500 to 3000 BCE. Firing clay bricks in a kiln transformed the chemical structure of the material, vitrifying the silica and creating a product as durable as stone. This was particularly vital in Mesopotamia, modern-day Iraq, and the Indus Valley, modern-day Pakistan, India, river civilizations that lacked the abundant stone quarries of Egypt. In Mesopotamia, the fired brick was a luxury item. Fuel for kilns was scarce, making fired bricks significantly more expensive than their sun-dried counterparts. Consequently, their use was restricted to the most critical parts of a structure: the foundations, the outer facings of ziggurats, and royal palaces, while the cores remained sun-dried mud. The durability of these fired ceramics allowed for monumental architecture that proclaimed the power of the state. The ziggurats, massive stepped pyramids, relied on the compressive strength of fired brick to support their enormous weight. Later, the Babylonians used glazed fired bricks to create the Ishtar Gate, a masterpiece of structural ceramics where the bricks were not only structural but also decorative, coated in deep blue lapis lazuli colored glazes and molded with reliefs of lions and dragons. This represents an early convergence of ceramic engineering and public art, asserting the permanence of the Babylonian Empire. In contrast to the monumental focus of Mesopotamia, the Indus Valley civilization, Harappa and Mohenjo-Daro, c. 2500 BCE, utilized fired brick for civic utility on a massive scale. The standardization of brick sizes in the Indus Valley was absolute. Bricks were produced in a perfect 1:2:4 ratio, roughly 7 × 14 × 28 centimeters, across an area of 1,000,000 square kilometers. The Indus engineers used these fired bricks to create the world's first sophisticated urban sanitation systems. The water resistance of fired ceramic was exploited to build waterproof bathing tanks, the Great Bath, lined wells, and elaborate covered drainage systems that ran beneath the streets. While sun-dried brick would have dissolved under constant contact with water, fired ceramic provided a chemically inert, impermeable barrier. This application of ceramics to public health allowed for high population densities in the tropical environment of the Indus floodplains, mitigating the disease risks inherent in early urbanization. Chemistry of the kiln, pyrotechnology, and the Greek miracle. The quality of any ceramic is dictated by the kiln. The earliest kilns were merely open bonfires or pit firings, reaching temperatures of only 600 to 800 degrees Celsius. These fires were inefficient and had uneven heat distribution, often resulting in high breakage rates and under-fired wares that remained porous. The first true innovation was the updraft kiln, appearing around 6000 to 3000 BCE in the Near East and China. In an updraft kiln, the fire is located in a firebox at the bottom, and heat rises through a perforated floor into a stacking chamber where the pottery sits, finally exiting through a vent at the top. This separation of fuel and wear protected the pottery from direct contact with the flames and allowed for higher, more consistent temperatures, up to 1000 degrees Celsius. Later, the downdraft kiln was developed and refined by the Romans and Chinese, where heat is drawn up over the ware and then pulled down through the floor into a chimney stack. This complex airflow retained heat longer within the chamber, improving fuel efficiency and ensuring an even firing temperature, crucial for high-quality ceramics. Nowhere was the mastery of kiln atmosphere more scientifically advanced in the ancient world than in classical Greece, circa 6th to 4th century BCE. The famous Attic black figure and red figure pottery was not produced using paints or pigments in the modern sense, but through a sophisticated manipulation of iron chemistry during a single firing cycle known as the three-phase firing. The paint used by Greek potters was simply a refined slip, liquid clay, with a very fine particle size, rich in iron, while the body of the vase was made of coarser clay. The visual contrast between the black and red areas was achieved by controlling the oxygen levels in the kiln. In oxidation phase, approximately 800 degrees Celsius, the kiln was fired with plenty of air intake, oxygen-rich. Both the pot and the slip turned red as the iron oxide converted to hematite, Fe2O3. In reduction phase, approximately 950 degrees Celsius, the potter closed the air vents and introduced damp wood or green brush. This produced smoke and carbon monoxide, CO, starving the kiln of oxygen. The red hematite lost oxygen and converted to black magnetite, Fe3O4, or iron oxide, FeO. Crucially, at this temperature, the fine particled slip sintered or partially vitrified, sealing its surface, while the porous body of the pot remained open. In reoxidation phase, approximately 900 degrees Celsius cooling, air was readmitted to the kiln. The porous body of the pot absorbed oxygen, turning the black magnetite back into red hematite. However, the sintered slip, having sealed itself during the reduction phase, could not reabsorb oxygen and remained permanently black. This process required empirical understanding of chemical reduction and precise control over kiln temperature and atmosphere. Recent studies using scanning electron microscopy, SEM, have even suggested that in some high-quality vessels, multiple firings or more complex slips with different melting points were used to achieve relief lines and specific sheens, indicating a level of technological sophistication bordering on nanotechnology. While the Greeks mastered chemistry, the Romans mastered scale. The defining ceramic of the Roman Empire was terra sigillata, often called Samian ware, characterized by its glossy red surface and relief decoration. The term terra sigillata means stamped clay or sealed earth. The glossy finish of terra sigillata was not a true glass glaze, but a sintered slip, similar to the Greek technique but refined for mass production. Roman potters created a slip of extremely fine clay particles by deflocculating clay in water and siphoning off the finest layer that settled between the water and the sludge. This fine slip, rich in silica and alumina, vitrified at a lower temperature than the body, creating a dense, shiny, waterproof coating without the need for burnishing. Production was organized on a truly industrial scale. At sites like Le Grau-Fessenc in southern Gaul, modern France, huge kilns were constructed that could fire up to 30,000 or 40,000 vessels in a single batch. Documentary evidence in the form of firing lists found at these sites confirms these staggering numbers. To achieve this, the kilns utilized a sophisticated system of clay tubes and pipes to funnel heat and smoke around the stacked pots, preventing the smoke from dulling the bright red color, a distinctive innovation over the open Greek firing. This standardized high-quality tableware was exported to every corner of the empire, from Hadrian's Wall in Britain to the deserts of Syria, serving as a marker of Roman cultural identity. Islamic Golden Age, Alchemy and the Luster of Invention. Following the collapse of Rome, the center of ceramic innovation shifted to the Islamic world, particularly during the Abbasid Caliphate, 750 to 1258 CE. The impetus for this innovation was trade. With the opening of maritime routes to Tang Dynasty China, Abbasid elites in Baghdad were exposed to white Chinese porcelain and stoneware. Lacking the specific kaolin-rich clays to reproduce porcelain, Iraqi potters used chemistry to imitate it. They developed tin opacified glazing. By adding tin oxide, SnO2, to a transparent lead glaze, they created an opaque, brilliant white surface that coated the local yellowish clay, successfully mimicking the appearance of Chinese porcelain. This technology, likely adapted from Egyptian and Roman glassmaking traditions, represents a significant leap in chemical engineering. The recipe for this white glaze spread rapidly from Iraq to Egypt, North Africa, and eventually to Spain, Al-Andalus, where it formed the basis of majolica and later Delftware. Concurrent with this was the development of opaque yellow glazes, particularly in Egypt and Syria, opacified with lead stannate or lead antimonate. These glazing technologies were not merely aesthetic, they were complex chemical formulations that required precise control over the lead-tin-silica ratios to prevent the opacifier from dissolving back into the glaze melt. The most technically complex contribution of Islamic ceramists was lusterware. This technique produced a metallic, iridescent sheen on the surface of the glaze, mimicking gold or silver. Its invention is closely linked to the practice of alchemy, the philosophical and proto-scientific pursuit of transmutation. Lusterware production involved a risky and difficult second firing. First, the vessel was fired with a standard glaze. Then, a mixture of metal salts, silver or copper oxides, sulfur, and ochre was painted onto the surface. The pot was returned to a kiln for a low-temperature firing in a heavy reduction atmosphere, starved of oxygen. The chemistry here is remarkable. The reducing atmosphere stripped the oxygen from the metal oxides, leaving behind a film of pure metal nanoparticles suspended in the glaze matrix. These nanoparticles were mere nanometers thick, so thin that they diffracted light, creating the shimmering, iridescent characteristic of lusterware. This was effectively the first practical application of nanotechnology. The process was so difficult and the knowledge so guarded that it remained a monopoly of a few families in centers like Kashan, Iran, and later Malaga, Spain. The exchange between China and the Islamic world was reciprocal. While the Middle East sought Chinese whiteness, China sought Persian blue. The cobalt pigment used to create the iconic blue and white porcelain of the Yuan and Ming dynasties was originally imported from Persia, known in China as sumali, or Hui Qing, Muslim blue. This imported cobalt was rich in iron, which caused the heaped and piled effect, dark, rust-colored spots where the pigment was applied thickly, a characteristic highly prized in early Ming wares. It was only later that China developed its own native cobalt sources, which were higher in manganese and produced a softer, grayish blue tone. The trade of cobalt for porcelain along the Silk Road is one of the earliest examples of a globalized industrial supply chain. Porcelain capital, Jingdezhen, and the Dragon Kiln. While the rest of the world struggled to imitate whiteness, the Chinese city of Jingdezhen had been perfecting true porcelain since the 10th century. The secret lay in the unique geology of the region, a combination of kaolin, a pure heat-resistant white clay, and patunci, pottery stone, a feldspathic rock that melts into a natural glass. When mixed and fired at temperatures exceeding 1250 degrees Celsius, the patunci melted and fused with the kaolin structure, creating a material that was white, translucent, and incredibly hard, vitrified like glass but strong like stone. The sheer scale of mining at Gaoling Mountain, the source of kaolin, was industrial. Excavations reveal quarry pits 50 meters deep, and the mountain eventually collapsed from exhaustion. To achieve the massive temperatures required for porcelain, Chinese engineers developed the Dragon Kiln, Longyao. These were long, tunnel-like structures built up the slopes of hills, resembling a dragon. They could be enormous, up to 60 meters long, and capable of firing 25,000 pieces of pottery in a single batch. The Dragon Kiln operated as a giant chimney. A fire was lit at the bottom, the head, and the hot gases rushed up the slope to the chimney at the tail. This natural draft created intense heat. Crucially, the kiln had stoke holes along its entire length, allowing potters to add wood at specific points to maintain temperature as the fire moved up the slope. This continuous large-scale processing capability allowed Jingdezhen to become the world's first true industrial city, producing millions of export ceramics centuries before the European Industrial Revolution. The value of this porcelain in Europe cannot be overstated. It was known as white gold. A testament to this obsession is the story of the dragoon vases. In 1717, Augustus the Strong, Elector of Saxony and King of Poland, was so possessed by porcelain fever, maladie de porcelain, that he traded a regiment of 600 fully equipped dragoon soldiers to King Frederick William I of Prussia in exchange for 151 pieces of Chinese porcelain, including 18 massive blue and white vases. This trade highlights the geopolitical weight of ceramics. A ruler traded his military power for fragile clay vessels, an act that underscores the desperate European desire to unlock the secret of porcelain production. Renaissance and European innovation, from Robbia to Palissy. While the Chinese perfected high-fire porcelain, the Italian Renaissance saw a revolution in low-fire terracotta. Luca della Robbia, 1399 to 1482, a Florentine sculptor, invented a method to apply the tin opacified glazes traditionally used on pottery to monumental terracotta sculpture. Robbia's technique involved creating a clay body rich in calcium, which was fired once, bisque, then coated in a glaze rich in lead and tin and fired again. The result was a sculpture with the brilliant, impermeable whiteness of marble, but the moldability of clay. This allowed for the creation of durable, weather-resistant outdoor art. His secret was closely guarded by his family for a century. Recent analysis suggests he may have used a third firing technique for gilding, similar to the Islamic lusterware tradition, highlighting the interconnectedness of ceramic technology. The desire to replicate Chinese porcelain led to the first European attempt, Medici porcelain, produced in Florence between 1575 and 1587 under Grand Duke Francesco I de' Medici. Lacking kaolin, the Medici alchemists used a soft paste recipe, a mixture of white clay from Vicenza, glass frit, and ground rock crystal. While it mimicked the translucency of porcelain, it was technically flawed. It warped in the kiln, was soft enough to be scratched with a knife, and had a cloudy glaze. Production ceased after Francesco's death, and only about 60 pieces survive today, serving as a testament to the difficulty of the material science involved. In France, the quest for ceramic perfection took a more legendary turn with Bernard Palissy, 1510 to 1590. A glass painter by trade, Palissy spent 16 years trying to discover the secret of white enamel. The legend, immortalized in Victorian Romanticism, holds that in his desperation to keep his kiln firing during a crucial experiment, he burned his own furniture and floorboards. While the furniture story may be apocryphal, his struggle was real. He eventually succeeded, not in making Chinese porcelain, but in creating rustic ware, dishes decorated with life-cast snakes, lizards, and ferns covered with brilliant colored glazes. Palissy's contribution was his empirical approach to glaze chemistry and his writings on geology and fossils. However, his Protestant faith led to his imprisonment in the Bastille, where he died, a martyr to both his religion and his art. Discovery of the Arcanum, Alchemists and Prisoners. The European breakthrough finally came in the early 18th century, and like the Medici attempt, it was driven by a ruler's obsession. Augustus the Strong, of dragoon vase fame, imprisoned a teenage alchemist named Johann Friedrich Böttger, who claimed he could turn lead into gold. When Böttger failed to produce gold, he was threatened with execution, but was saved by the intervention of the scientist Ehrenfried Walter von Schönhaus, who directed him toward the white gold of porcelain. Schönhaus approached the problem scientifically, using burning mirrors to test the melting points of various minerals. Böttger, applying his alchemical rigor to clay, realized that the secret lay not in glass, as in soft paste, but in finding a refractory material that could withstand intense heat, mixed with a flux that would vitrify it. In 1708, using clay from Colditz and alabaster as a flux, they produced a hard red stoneware, Böttger stoneware, that was incredibly dense and could be polished like a gemstone. Soon after, by substituting the red clay with white kaolin found at Au, Böttger unlocked the Arcanum, the formula for true, white, hard porcelain. Schönhaus died in 1708, and Böttger announced the discovery to Augustus in 1709. The Meissen factory was established in 1710, the first in Europe to produce true porcelain. Böttger remained a prisoner of the state, guarding the secret until his death, his life consumed by the material he mastered. Industrial Revolution, Wedgwood, and the science of manufacturing. While Böttger discovered the chemistry, Josiah Wedgwood, 1730 to 1795, industrialized the process. Operating in Staffordshire, England, Wedgwood transformed pottery from a craft into a manufacturing empire. He was a key figure of the Industrial Revolution and a member of the Lunar Society, alongside figures like James Watt and Erasmus Darwin. Wedgwood introduced the division of labor to pottery. Previously, one potter would make a pot from start to finish. Wedgwood split the process: throwers, turners, handlers, and painters. This specialization increased speed and consistency, a precursor to the assembly line. He also utilized the steam engine to grind materials and drive machinery. Wedgwood was also a scientist. He struggled to measure the extreme temperatures inside his kilns, as mercury thermometers would explode. He observed that clay shrinks predictably when heated. He invented the pyrometer, a device that measured the shrinkage of standard clay cylinders to determine kiln temperature. This invention was so significant, he was elected to the Royal Society. His crowning aesthetic achievement was jasperware, a dense, unglazed stoneware, usually in blue or Wedgwood blue, with white reliefs. The secret ingredient was barium sulfate, caulk, a mineral found in lead mines. After thousands of experiments recorded in his notebooks, he perfected the formula: roughly 57% barium sulfate, 29% ball clay, 10% flint, and 4% barium carbonate. This material was so hard it could be polished on a lapidary wheel, bridging the gap between pottery and gemstone. Wedgwood also revolutionized transport. Ceramics are heavy and fragile, terrible for bumpy horse-drawn carts. Wedgwood lobbied for and invested in the Trent and Mersey Canal, which connected his factory, Etruria, to the ports of Liverpool, reducing breakage rates and transport costs effectively to zero compared to road haulage. Sanitation and steel. Ceramics as engineering infrastructure. In the mid-19th century, London was the largest city in the world, and it was drowning in filth. Cesspools leaked into the groundwater, and raw sewage flowed into the Thames, the city's drinking water source. This led to cholera epidemics that killed thousands. The crisis culminated in the Great Stink of 1858, when the smell of the river was so noxious that Parliament nearly abandoned Westminster. The solution was a massive new sewer network, engineered by Joseph Bazalgette. The critical material that made this possible was the salt-glazed stoneware pipe manufactured by Henry Doulton. Unlike porous brick tunnels or rotting wood, Doulton's Keramec pipes were impervious to chemical attack, waterproof, and smooth enough to prevent blockages. Doulton's Lambeth factory produced miles of these pipes, effectively sanitation-proofing the modern metropolis. Doulton also developed the ceramic water filter, using diatomaceous earth in collaboration with Louis Pasteur's research on bacteria. These porous ceramic filters could physically trap bacteria, providing safe drinking water to the British Empire's troops and hospitals. The Industrial Revolution was built on steel, and steel is built on ceramics. To melt iron and refine steel, furnaces must withstand temperatures that would melt almost any other material. This required advanced refractory ceramics. The Bessemer converter, invented 1856, which allowed for mass production of steel, relied on specific ceramic linings. The process was originally acidic, using silica bricks made from quartzite and lime, which could withstand heat but could not remove phosphorus from the iron. This limited steelmaking to phosphorus-free ores. The breakthrough came with the basic process, Thomas Gilchrist process, which lined the converter with dolomite bricks, magnesium calcium carbonate. The basic chemistry of the dolomite lining reacted with the acidic phosphorus in the iron, removing it as slag. This ceramic innovation allowed the vast phosphorus-rich iron ore deposits of Europe and America to be exploited, dramatically lowering the cost of steel and fueling the construction of railroads and skyscrapers. Electrical age. Porcelain insulators. As the 19th century closed, a new invisible force, electricity, needed containment. The telegraph system had largely used glass insulators, which were cheap and sufficient for low-voltage batteries. However, as high-voltage power transmission began, example the Niagara Falls to Buffalo line in 1996, glass failed. It attracted moisture, was too brittle for the heavy copper cables, and shattered under electrical stress. The solution was wet process porcelain. Fred M. Locke, a telegraph operator turned inventor in Victor, New York, realized that standard dry press porcelain, pressed clay dust, was too porous and absorbed water, leading to electrical leakage. He developed a wet process technique, where the clay was mixed into a plastic state, molded, and fired at high temperatures to fully vitrify it. Locke's wet process porcelain, glazed to shed water, and designed with petticoats or flared skirts to increase the surface distance between the wire and the pin, made high-voltage transmission possible. The Niagara line, using Locke's porcelain designs, proved that electricity could be moved over long distances, inaugurating the age of the electrical grid. While the pottery of antiquity defined culture through storage and art, the advanced ceramics of the modern era define civilization through survival, computation, and exploration. This part provides an exhaustive analysis of the transformation of ceramics from traditional earthenware to the high-performance oxides, carbides, and nitrides that underpin the modern world. This revolution was not driven by the potter's wheel, but by the existential pressures of the Cold War, the thermal violence of atmospheric re-entry, and the nanoscopic demands of the semiconductor industry. Unlike metals, which share electrons in a sea that grants ductility, ceramics are defined by rigid ionic and covalent bonds. It is this atomic stubbornness, this refusal to yield to heat, electricity, or kinetic impact that has made them indispensable. From the boron carbide armor that shielded pilots in Vietnam, to the silicon carbide inverters propelling today's electric vehicles, ceramics have served as the silent sentinels of technological progress. This part traces that trajectory, revealing how a class of materials once synonymous with fragility became the backbone of the most extreme engineering challenges in history: Cold War defense and ballistics. The transition from traditional to advanced ceramics was accelerated by the geopolitical tensions of the mid-20th century. The Cold War created a strategic imperative for materials that could withstand high-velocity projectiles without the prohibitive weight of thick steel plating. The fundamental advantage of ceramics in armor systems lies in their high hardness and low density relative to metals. This section explores how the physics of fracture mechanics replaced the physics of plastic deformation in the philosophy of defense. Historically, armor relied on the ductility of metals to absorb energy. A steel plate would deform, stretching and bulging to catch a bullet. However, as ballistic technology advanced, projectiles became faster and harder, capable of piercing steel with ease. The Cold War demanded a new paradigm. The answer lay in the unique mechanics of ceramic fracture. When a high-velocity projectile strikes a ceramic plate, the material does not yield, it shatters. The ceramic face acts as a dwell surface, arresting the projectile for microseconds and forcing it to expend its kinetic energy on self-destruction. The tip of the bullet is blunted or shattered against the ceramic's extreme hardness, dispersing the impact energy radially rather than allowing it to penetrate linearly. This shift began in earnest during World War I with experiments in enameling steel, but the true ceramic age of defense arrived with the Vietnam conflict. The dense jungles and mobile warfare of Vietnam necessitated lightweight protection, particularly for helicopter crews vulnerable to ground fire. The solution was boron carbide, one of the hardest materials known to science. Integrated into the seats of helicopters, boron carbide plates provided the first widespread operational use of monolithic ceramic armor. This application highlighted the critical engineering trade-off that defines ceramic armor: brittleness versus hardness. While boron carbide offered exceptional weight savings, crucial for rotary wing aircraft, where every pound affects lift and range, its high cost and processing difficulties limited its widespread use to these critical, high-value areas. Over the ensuing decades, the defense industry refined a tiered system of ceramic materials, balancing ballistic performance against weight and manufacturing cost. This material hierarchy remains in place today, dictating the composition of everything from tank armor to personal protective equipment. Alumina emerged as the workhorse of the ceramic armor industry. While it possesses the highest density of the common ballistic ceramics, approximately 3.9 grams per centimeter cubed, its relatively low cost and established manufacturing infrastructure made it the default choice for vehicle armor and static defense structures. Rudimentary alumina ceramics were used in the 1960s primarily for heat shielding, but by the 1990s, advancements in processing allowed for high-purity, high-density alumina tiles capable of stopping small arms fire. Its economic viability ensures it remains the most widely used ceramic in defense, balancing adequate performance with mass producibility. Occupying the middle ground is silicon carbide. With a density of approximately 3.2 grams per centimeter cubed, SiC offers a significant weight advantage over alumina, while boasting superior hardness and ballistic performance. However, SiC is more expensive to produce, requiring higher sintering temperatures and more complex raw material synthesis. It became the material of choice for applications where the weight penalty of alumina was unacceptable, but the extreme cost of boron carbide could not be justified, such as in the armor of light tactical vehicles and upgraded personal body armor plates. At the top of the pyramid sits boron carbide. With a density of roughly 2.5 grams per centimeter cubed, lighter than aluminum, yet harder than almost any other industrial ceramic, it is the material of choice for weight-critical applications. In personal body armor, where soldier mobility is paramount, and in aerospace components like the C-130 Hercules armor upgrades, boron carbide is indispensable despite its high cost. Modern research has moved beyond simple monolithic plates to sophisticated ceramic matrix composites. The 1980s marked a pivotal shift with the integration of these composites into vehicle armor, significantly enhancing protection while reducing weight compared to traditional steel. A prime example involves the incorporation of SiC particles into an alumina matrix. This dispersion creates a composite that retains the cost-effectiveness of alumina while benefiting from the hardness of silicon carbide, reportedly reducing density and increasing fracture toughness. The brittleness of ceramics has historically been their Achilles heel. A single impact could shatter a plate, leaving the user vulnerable to subsequent hits. The early 2000s witnessed the emergence of nano-engineered ceramics designed to address this vulnerability. By refining grain structures to the nanometer scale and introducing second-phase toughening agents, engineers created materials with improved multi-hit capability. These advanced ceramics can withstand an initial impact without catastrophic failure of the entire plate, maintaining structural integrity for subsequent threats. Current military technology encompasses this diverse range of materials: aluminum oxide, silicon carbide, boron carbide, and silicon nitride, each optimized for specific operational envelopes ranging from personal body armor to missile radomes. Nuclear crucible. Parallel to the ballistic developments of the Cold War, the dawn of the nuclear age in the 1950s created a demand for materials capable of surviving intense radiation, chemical reactivity, and extreme thermal gradients. The nuclear reactor is arguably the most hostile environment on Earth for a material, and ceramics prove to be the only class of matter capable of containment. The heart of a nuclear reactor is its fuel. While early experimental reactors utilized metal fuels, the industry quickly standardized on ceramic uranium dioxide pellets. The logic was simple: thermal stability. Metallic uranium melts at 1,132 degrees Celsius and swells unpredictably under irradiation. In contrast, ceramic uranium dioxide has a melting point of 2,847 degrees Celsius, a massive safety margin for reactor operation. The open crystal structure of oxide ceramics provided another critical advantage: the ability to retain fission product gases. As uranium atoms split, they generate gaseous byproducts like xenon and krypton. In a metallic lattice, these gases form bubbles that cause the fuel to swell and deform, potentially blocking coolant channels. The ceramic lattice of uranium dioxide, however, can accommodate these fission products within its structure or grain boundaries without catastrophic swelling. This dimensional stability allows fuel rods to remain in the reactor for years. The fabrication of these pellets is a triumph of ceramic engineering. The process involves comminution, grinding of uranium oxide powder, granulation, pressing into cylindrical pellets, and sintering at 1,700 degrees Celsius in a reducing atmosphere. The result is a high-density, refractory ceramic that serves as the first and most critical barrier against the release of radioactive material. The Cold War drive for nuclear supremacy pushed ceramic research into even more extreme territories. In the 1950s and 60s, the US government conducted a series of bold experiments to test the limits of nuclear technology. The Boiling Water Reactor Experiment Number 4, or Borax IV, tested fuel elements made from mixed oxides of uranium and thorium. These ceramic fuels were designed to operate longer in the reactor's extreme heat before failing, proving the viability of ceramic compositions beyond simple uranium dioxide. Concurrently, the Aircraft Nuclear Propulsion Program sought to build a nuclear-powered jet airplane, a concept that required a reactor to operate at the temperatures of a jet engine. The Heat Transfer Reactor Experiments, HTRE-1 and later HTRE number 2, advanced the technology of high-heat ceramic reactor fuels, testing hexagonal ceramic fuel elements capable of withstanding the immense thermal stresses of air-cooled nuclear propulsion. Although the program was canceled by President Kennedy in 1961, the materials science developed for HTRE laid the groundwork for future high-temperature gas-cooled reactors. The persistence of nuclear waste prompted the development of ceramic waste forms to secure the atomic legacy. While borosilicate glass, or vitrification, became the standard for high-level waste, it is technically a glass, not a crystalline ceramic. A more durable alternative, known as synrock, synthetic rock, was developed to mimic natural minerals that have geologically retained radioactive elements for millions of years. Synrock relies on the principle of isomorphism. Radioactive ions are incorporated directly into the crystal lattice of titanate ceramics, effectively locking them in a mineral prison. This creates a waste form that is extremely resistant to leaching, even in the presence of groundwater at elevated temperatures, ensuring the long-term isolation of high-level waste far more effectively than glass or cement. Rocketry and Spaceflight. If the Cold War provided the impetus for ballistic ceramics, the space race provided the thermal challenge. Rocketry and re-entry vehicles operate in environments where temperatures exceed the melting points of most superalloys, necessitating the use of refractory ceramics that can insulate, radiate, and survive. Perhaps the most iconic application of advanced ceramics is the Thermal Protection System, or TPS, of the NASA Space Shuttle. Re-entering Earth's atmosphere at Mach 25 generates shock waves that heat the air to plasma, creating surface temperatures on the orbiter of up to 1,650 degrees Celsius, or 3,000 degrees Fahrenheit. The requirement was for a heat shield that was not only refractory, but also reusable and lightweight, a combination that ruled out the ablative shields used on the Apollo capsules. The solution, developed largely by Lockheed Missiles and Space Company, involved high-temperature reusable surface insulation, or HRSI tiles. These tiles were not solid blocks of ceramic, but highly porous structures composed of high-purity silica fibers derived from sand. The primary tile used, designated Li 900, had a density of only 9 pounds per cubic foot. Astoundingly, these tiles were 90% air and only 10% silica glass fibers. This extreme porosity made them exceptional insulators. A tile could be red hot in the center, while the edges remained cool enough to hold with bare hands, preventing the heat from conducting through to the aluminum skin of the shuttle. However, pure silica is white and transparent to heat radiation, and the porous structure is fragile. To solve this, the tiles were coated with a reaction-cured glass, or RCG, a black borosilicate glass containing silicon tetraboride. This black coating served two purposes. It provided a tough, moisture-resistant skin, and its high emittance allowed the tiles to efficiently radiate re-entry heat back into space. The development was fraught with challenges. One major issue was the densification problem. The tiles were so porous that the bond between the tile and the felt strain isolator pad was weak, leading to tile detachment. The engineering fix involved impregnating the inner mold line of the tiles with a silica slurry, a mixture of Ludox colloidal silica and silica particles, to create a denser, stronger interface layer. This densification process was retrofitted to thousands of tiles on the Columbia orbiter, a massive undertaking that ensured the system's structural integrity. Beyond heat shields, the propulsion systems of rockets required materials that could survive the chemical violence of combustion. Silicon nitride, first synthesized in the mid-19th century but not commercialized until the 1950s, became a critical material for these applications. Unlike metals, which soften and lose strength at high temperatures, silicon nitride maintains its mechanical strength up to 1200 degrees Celsius. Its low thermal expansion coefficient and high fracture toughness make it ideal for components subjected to extreme thermal shock, such as rocket nozzles and thrusters. A notable example is its use in the thrusters of the Japanese space probe Akatsuki, where it withstood the rigors of orbital insertion. The material is also used in the cryogenic pump bearings of the Space Shuttle main engines, demonstrating its versatility from extreme cold to extreme heat. As aerospace engineering pushes toward hypersonic flight, Mach 5+, even silica and silicon nitride become insufficient. The aerodynamic heating at the sharp leading edges of hypersonic vehicles can exceed 2,000 degrees Celsius, a regime where silica would soften and fail. This has led to the resurgence of ultra-high temperature ceramics, or UHTCs, specifically the diborides of hafnium and zirconium. These materials are unique, with melting points above 3,200 degrees Celsius. They are among the most refractory substances known. Crucially, they possess a combination of metallic-like thermal conductivity and ceramic hardness. This high thermal conductivity is vital for sharp leading edges. It allows the intense heat generated at the stagnation point, the very tip of the wing or nose, to be conducted back into the bulk of the material, effectively wicking the heat away and preventing localized melting. current research focuses on overcoming the oxidation limits of these materials. While they resist melting, they can oxidize in the high-temperature plasma of hypersonic flight. To combat this, researchers add silicon carbide, or SiC, to the diboride matrix. At high temperatures, the SiC oxidizes to form a protective glassy scale of silica that seals the surface and prevents further degradation of the underlying material. This dynamic oxidation protection is a key enabler for the next generation of hypersonic missiles and spaceplanes. Electronics, packaging, and miniaturization. While aerospace and nuclear applications showcase the macro strength of ceramics, the micro capabilities were revealed by the electronics revolution. The miniaturization of electronics, from the clunky vacuum tubes of the 1940s to the microprocessors of today, was fundamentally enabled by ceramic substrates and packaging. Aluminum oxide, alumina, is the foundational material of the electronics industry. While silicon gets the glory for the transistor, alumina provided the stage upon which the silicon revolution was built. Its high electrical resistivity combined with good thermal conductivity, 20 to 30 watts per meter Kelvin, makes it the ideal substrate for integrated circuits. In the early days of electronics, the heat generated by components was a limiting factor. Aluminous substrates acted as heat sinks, drawing thermal energy away from active devices like resistors and transistors, preventing failure. Furthermore, the dimensional stability of alumina during thermal cycling, it expands and contracts very little, ensured that the delicate conductive pathways printed on them did not crack or delaminate. This stability was crucial for the development of hybrid integrated circuits, where resistors and capacitors were printed directly onto the ceramic surface. The packaging of integrated circuits, the physical housing that connects the microscopic chip to the macroscopic circuit board, has evolved through several ceramic-dependent iterations. In the 1960s and 70s, the ceramic dual inline package, CERDIP, became the standard for high-reliability electronics. Invented at Fairchild Semiconductor, these packages used a ceramic base and lid sealed with glass to provide a hermetic environment for the silicon die. This hermetic seal was crucial for military and aerospace applications, where moisture ingress could cause corrosion and failure. The rise of companies like Kyocera, originally Kyoto Ceramic Co., was driven by this demand. Recognizing that the U.S. semiconductor industry needed specialized packaging, Kyocera focused on high-quality ceramic components, eventually becoming a dominant supplier of semiconductor packages. Their first product, the Kelsima ceramic insulator for cathode ray tubes, paved the way for their dominance in IC packaging. As processing speeds increased, the industry developed co-fired ceramics technology. High-temperature co-fired ceramics, HTTC, centered above 1500 degrees Celsius, offered high mechanical strength, but limited the choice of conductors to high melting point metals like tungsten and molybdenum, which have higher electrical resistance. This was a bottleneck for high-speed signal transmission. To overcome this, low-temperature co-fired ceramics were developed. By adding glass to the ceramic matrix, the sintering temperature was lowered to below 900 degrees Celsius. This allowed for the use of highly conductive metals like gold, silver, and copper for the internal wiring. LTCC became the standard for high-frequency applications, such as radar modules and mobile phone components, where signal loss must be minimized. The miniaturization of mobile devices, smartphones, laptops, and wearables relies heavily on the multi-layer ceramic capacitor, MLCC. A modern smartphone may contain over 1,000 of these tiny components to regulate power and filter signals. The development of MLCCs followed a Moore's law of its own. In the 1980s, a standard capacitor was the 3216 size, 3.2 by 1.6 millimeters. Today, the 0603 size, 0.6 by 0.3 millimeters, smaller than a grain of sand, delivers the same capacitance. This was achieved by developing ultra-thin dielectric ceramic layers, often less than 1 micron thick, and stacking hundreds of them to maximize surface area within a microscopic volume. This stacking technology relies on precise nanotechnology to disperse dielectric and nickel particles, a feat of ceramic engineering that underpins the entire portable electronics market. The manufacturing process involves casting a slurry of ceramic powder into a thin green sheet, printing electrodes on it, stacking hundreds of layers, and sintering them into a solid rock-like chip. Rise of silicon carbide. As the world transitions to electric mobility, a new ceramic hero has emerged: silicon carbide, SiC. While SiC has been used as an abrasive since the days of Edward Acheson in the 1890s, its potential as a semiconductor was realized much later. Today, it is the key enabler of long-range electric vehicles and fast charging. Traditional power electronics use silicon, Si. However, silicon hits physical limits at high voltages and temperatures. Silicon carbide is a wide bandgap semiconductor, 3.26 eV versus 1.12 eV for silicon, meaning it requires more energy to excite an electron from the valence band to the conduction band. This atomic property translates to massive real-world advantages for electric vehicles. SiC can withstand 10 times the breakdown electric field of silicon. This allows for thinner, more efficient devices that can handle the 800-volt architectures of modern EVs. SiC has 3 times the thermal conductivity of silicon. It can operate at higher temperatures, reducing the need for heavy, complex liquid cooling systems. SiC switches, MOSFETs, can turn on and off much faster than silicon IGBTs with significantly less energy loss. This efficiency directly translates to increased range for the vehicle. The automotive industry's SiC moment arrived with the introduction of Tesla Model 3. Tesla became the first high-volume manufacturer to integrate a full SiC inverter, developed in collaboration with ST Microelectronics. Historically, inverters used silicon IGBTs. By switching to SiC MOSFETs, Tesla achieved a significant reduction in conduction and switching losses. The inverter design features 24 power modules mounted on a pin-thin heatsink, a compact architecture made possible only by the thermal resilience and high efficiency of SiC. This innovation allowed Tesla to optimize the size of the cooling system and the battery, creating a lighter, more efficient vehicle. The success of the Model 3 forced the rest of the automotive industry to accelerate their adoption of SiC, cementing it as the critical material for the future of green energy. From inert to bioactive. The chemical inertness that makes ceramics ideal for nuclear waste also makes them perfect for the harsh environment of the human body. Bioceramics have evolved from bio-inert space fillers to bioactive scaffolds that encourage tissue regeneration. For decades, titanium was the gold standard for dental implants due to its ability to osseointegrate, fuse with bone. However, the demand for metal-free aesthetics and concerns over metal sensitivity led to the rise of zirconia ceramics. Zirconia, often called ceramic steel, offers high fracture toughness and a white color that mimics natural teeth. This is a crucial aesthetic advantage over titanium, which can cast a gray shadow through thin gum tissue. Early concerns about the osseointegration of zirconia, whether bone would bond to it as well as titanium, have been largely addressed through surface modifications. By creating micro-roughness on the zirconia surface, manufacturers have improved bone cell attachment. Clinical studies now show that zirconia implants have survival rates comparable to titanium, with the added benefit of lower plaque accumulation and reduced inflammatory response. Beyond structural implants, calcium phosphate ceramics like hydroapatite, HA, have revolutionized bone grafting. Since HA is chemically similar to the mineral component of human bone, it is not rejected by the body. Instead, it acts as an osseo-conductive scaffold. When placed in a bone defect, HA provides a structure for new bone cells to climb on. Modern research has led to third-generation porous bioceramics that are bioresorbable. These materials provide temporary support while the body heals. Over time, the ceramic dissolves and is entirely replaced by natural bone, leaving no foreign material behind. This concept of materials that disappear represents the ultimate goal of regenerative medicine. Everyday toughness, the science of Gorilla Glass. In the consumer realm, the most visible application of advanced ceramics is the cover glass of smartphones. Corning's Gorilla Glass represents a triumph of chemical strengthening known as ion exchange, a technology rooted in research from the 1960s. Glass is inherently brittle because microscopic surface flaws can propagate into cracks under tension. To counteract this, Gorilla Glass, an alkali aluminosilicate composition, is chemically strengthened. The glass is immersed in a bath of molten potassium salt at approximately 400 degrees Celsius. During this bath, a chemical swap occurs. Smaller sodium ions leave the glass structure and are replaced by larger potassium ions from the salt. Because the potassium ions are physically larger, they wedge themselves into the glass surface, creating a layer of compressive stress. This compressive skin acts as a shield. For a crack to propagate, it must first overcome this compressive force. This mechanism allows the glass to remain thin and lightweight while resisting the scratches and drops of daily use. Corning originally developed this technology in 1960 under the name ChemCore for a project called Project Muscle, but it found no market until the advent of the iPhone and the modern smartphone era. Future frontiers: intelligence, fabrication, and self-healing. The future of ceramics lies in dynamic properties and novel fabrication methods that overcome the traditional limitations of shaping and brittleness. The next generation of ceramics will not just sit there, they will heal, adapt, and compute. One of the most exciting areas of research is oxidation-induced self-healing. Ceramics are prone to cracking, and catastrophic failure often results from the propagation of microscopic surface flaws. New composite ceramics, such as those containing silicon carbide particles, utilize the very environment that usually degrades materials, oxygen, to heal themselves. When a crack forms, the exposed silicon carbide particles react with oxygen at high temperatures to form silicon dioxide and volume-expanding oxides. This oxide phase expands to fill the crack volume, effectively gluing the surfaces back together. Researchers are now developing healing activators like manganese oxide that lower the temperature required for this reaction, allowing the healing to occur at typical operating temperatures of turbine engines. This technology promises to extend the lifespan of turbine blades and aircraft components significantly, turning the material's reaction to the environment into a survival mechanism. Historically, ceramics were difficult to shape into complex geometries due to the need for molds and machining diamond tools. Additive manufacturing, AM, particularly stereolithography, SLA, is changing this. By using photosensitive resins loaded with ceramic powders, engineers can print complex lattice structures and internal cooling channels that were previously impossible to cast. However, challenges remain, particularly with dark ceramics like silicon carbide. These materials absorb the UV light used to cure the resin, preventing the formation of thick layers. Innovations in slurry formulation and light intensity control are slowly overcoming these barriers. The ability to print ceramic parts allows for origami-inspired metamaterials, structures that derive strength and flexibility from their geometry rather than just the material properties. This is opening doors for custom medical implants and advanced hypersonic engine parts that are lighter and more efficient than any cast component. As the limits of organic substrates are reached in high-performance computing, AI, and data centers, the industry is pivoting toward glass core substrates. Intel and other major players are developing glass substrates that offer superior flatness and thermal stability compared to organic materials. Glass allows for much finer interconnects, high density, and better dimensional stability, which is critical for the massive system-in-package chipsets required for AI training. Unlike organic substrates, which can warp during the heat of manufacturing, glass remains flat, allowing for more precise lithography and denser wiring. This shift represents a return to ceramic-like materials, glass, to solve the bottlenecks of the silicon age, ensuring that Moore's Law can continue into the era of artificial intelligence. The history of ceramics is a narrative of human ingenuity mastering the Earth's most stubborn materials. From the enameling of World War I armor to the self-healing turbine blades of the future, ceramics have evolved from passive structural blocks to active, functional systems. The Cold War and the space race necessitated this shift, pushing material science to conquer the extremes of ballistic impact and re-entry heat. Today, the digital revolution and the green energy transition are sustaining this momentum. Whether in the form of a microscopic capacitor in a smartphone, a silicon carbide inverter in an electric car, or a zirconia implant in a human jaw, advanced ceramics have become the invisible infrastructure of modern life. They are the materials that allow us to touch the screen of the world's knowledge, to fly at hypersonic speeds, and to harness the power of the atom. As we look to the future, towards self-repairing engines and AI supercomputers, it is clear that the Stone Age never truly ended, it just became high-tech. The clay of the past has become the carbide of the future, and the kiln has been replaced by the precision of the laser and the plasma torch.